Hello everybody, I hope you all are okay and you all are safe wherever you are. As you all have already seen the trial um, video uh, for the online lecture, I did that one in the classroom on campus, but things could change in a moment, and I'm not sure that I would be able to uh, go to campus and do the recording. So I decided to set up a kind of lecture classroom here, my home in in, a, in my garage. So this is the uh, kind of lecture classroom. So you may see these different patches that I put on the board, the blue one. So this is just to avoid a glare that comes from the fluorescent light, so that I wouldn't write here. If I write here, you wouldn't be able to see it. So that's why I put these different patches that you see here on the board. So all this, okay, and here, okay. So I'm going to start the first online lecture for mathematical methods in theoretical physics 2 from wherever we stopped last time. Okay, last time we talked about the method of Frobenius for solving differential equations, and we considered the Bessel differential equation, and we found the solution, which was the Bessel functions. So today what we will see is, like the solution to the legendary differential equation, where we have the legendary polynomials, or solutions to the associated legendary differential equation, where we have the associated legendary polynomials. We saw the orthogonality relations for the legendary polynomials, or for the associated legendary polynomials, or even for spherical harmonics. We have seen the orthogonality relations. So today what we will see is the orthogonality relation for the solution to the Bessel differential equation, which are the Bessel functions. So we will talk about the solution, we will talk about the orthogonality relation for the Bessel function. Okay, so that's what we will do today. Right, so hopefully you would be able to see what I write on the board here, and also what I'm going to show you here on the screen. So this is probably better if I turn off the light. But before I do that, so every time when I point to the PDF file on the screen here, which is my note, I will turn off the light. So every time when I write on the board here, I will turn the light on. All right. And if you can see what I am pointing here on the screen, I suggest you to download the PDF file um, um, the most updated one, and follow me while I'm pointing on the screen here. I'll try to tell you the page number and also, you know, the equations number, whichever equations I'm referring to. All right. So 12, 11, 11, the orthogonality of the Bessel functions. So we recall the Bessel differential equation, which is, we recall the Bessel differential equation, which is given by x squared d squared y by dx squared plus x dy by dx plus x squared minus p squared y equals to 0. So last time, using the method of Frobenius, we have shown that the solution is the Bessel function. The Bessel function, which we represented by Jp of x. Okay, so what we will try to see today is what is the orthogonality relation for these Bessel functions, just like the legendary polynomials or the spherical harmonies or the associated legendary polynomials. What is the orthogonality relation for these Bessel functions? So to this end, first we need to merge these two terms in the differential equation. So what I'm going to do is I apply the product rule. The product rule for these two terms, this and that, and I can put, okay, so I can put these two terms using the product rule in the following form. So x squared d squared y by dx squared plus x dy by dx. So this, if I factor out x from both terms, I would have x times x dy by dx plus dy by dx. Okay, so I just factored out x from both terms, and I can merge these two if I apply the product rule, which is going to be x d by dx of x dy by dx. So, you know, according to the product rule, if you expand this, this means the derivative of x with respect to x times by dy by dx, which is going to be, so the derivative of this times by that, so the derivative of x with respect to x, that's 1, so you have dy by dx, and the derivative of this times by that, so plus x d squared y by dx squared. Okay, So it's just a simple product rule. So then I can rewrite, so I will call this one is equation 1. So applying the product rule, we merge these two into that, and I can substitute that into equation. So substitute this into equation 1. So if I substitute that in place of these two terms in this equation, what I would find is going to be x d by dx, x dy by dx, plus x squared minus p squared y equals to 0. All right, so that's what we get for the differential equation. Okay, now suppose I introduce a variable, or suppose if I replace x by u, I can write this differential equation. So for a differential equation, so instead of x, let's say we have u. So u d by dx, by du, u dy by dx, by du, plus u squared minus p squared y equals to 0. So now y is a function of now it's a function of u. Okay, as you know, the only thing that we change it is x to u. All right, so what's the solution of this differential equation? It's the Bessel function. What that means is that, in terms of the Bessel function, then since the solution of this is a Bessel function, what it means is that y of u is j of u. Okay, so of course p. So this means I can write this differential equation in the following form. So u d by du, u djp of u by du, plus u squared minus p squared jp of u equals to 0. Okay, since the solution to the Bessel differential equation is the Bessel function. Okay, all right, so now next what I'm going to do is I'm going to relate u and x by the following equation. Okay, so if I let say u equals to alpha I x. So what's alpha I? All right, so alpha I is the zeros of the Bessel function. What does that mean? Okay, in order to explain that, I need to show you on the screen in my notes for the graph of jp of x versus x. So for that, I'm going to turn off the light here. Okay, so hopefully, well, it's probably, that's not a good thing. Oh man. All right. So let's try this. So if I make it bigger, so if you recall, so this is the graph So I don't know if you can see it. So this is on page. So this is on page 370, figure 1210. Okay. So this is the graph of JP of x versus x. So for example, for p equals to 0, you can see this, the red graph, and it becomes JP of x equals to 0 at x equals to alpha 1, alpha 2, alpha 3. And for p equals to 3, it becomes 0 at similarly alpha 1, alpha 2. And the same for p equals to 6. So we represent the point at which the function becomes 0, the value of x at which JP of x becomes 0, we call it the zeros of the Bessel function. So that is what alpha I represent. So so this thing forgets me to follow. Okay. All right. So where alpha I equals to alpha 1, alpha 2, alpha 3, and so on are the zeros of the Bessel function. Okay? So if I introduce this variable, then du is gonna be d of alpha I x. Since alpha I is a constant, so this is gonna be the same as alpha I dx. Okay? So we substitute this and this into this equation, which I call it equation 2. So we substitute these two relations into equation 2, then you would find this equation. So what you'd find is going to be, so what you'd find is going to be x d by dx, x dj p. Now remember, u is defined in terms of the zeros of the Bessel function. So jp is going to be a function of alpha I x by dx plus, in place of u again, in place of u I have alpha I x. So that's going to be alpha I squared x squared minus p squared times jp of alpha I x. That is equals to 0. Okay? Okay, now here I defined u as alpha I x. But you know, I can define it as alpha jx. So for u equals to alpha jx, one can also write, or we can write, so the only thing that would change is alpha I becomes alpha j. So we have this equation, x d by dx, x djp alpha jx by dx plus, instead of alpha I would have alpha j squared x squared minus p squared jp alpha jx equals to 0. So I have these two equations. So we have here equation 2. Now I will call this one equation 3 and this one equation 4. Okay? All right. So I'm going to pause here and then we will continue from this.